The question that I have is, could you do an example on friction involving a wedge? This is the problem that I have chosen here. We have a block that is to be moved either vertically up or down using a single wedge like shown in this picture. The wedge has an inclined plane that makes an angle of 30 degrees to horizontal. The weight of the block is 4,000 Newton. The wedge makes contact with the block and the floor, and the block makes contact with this vertical wall and the wedge. There are three frictional surfaces of interest to this problem: this vertical wall, this interface between the block and the wedge, and the floor, right? The values of the coefficient of friction for these three frictional surfaces are given. The question is to determine the value of P needed, part A, for lifting the block by pushing the wedge in, and part B for lowering the block by pulling the wedge out. Since there are lots of similarities between the two parts of the problem, we'll do them side by side here. This column right here is for lifting the block, and this column is for lowering the block. Remember, the first step is to understand the mechanism, right? This would allow us to determine the direction of the frictional forces. Let's consider the problem of lifting the block first. The wedge and the block are considered to be rigid bodies, right? So what I'm trying to do here is to mark the directions of the movement of these rigid bodies. We know the wedge moves horizontally to the right, left to right, right? And the block moves vertically up, right? Like shown, like indicated by this arrow right there. And of course the floor is stationary and the wall is stationary, right? And this allows us to evaluate the relative movement of a point on an interface. Let's consider the wedge for a second here. So the wedge, we know, is a rigid body and it moves horizontally like this, right? So that means every point on the wedge moves horizontally, right? And therefore, if I consider a point at the interface between the block and the wedge, but on the wedge, that point is going to be moving in that direction, right? Okay? And similarly, if I consider a point on the wedge, but at the interface between the wedge and the floor, that point, which is on the wedge, right, is going to be moving like this, right? So this is basically same as that, but this is the component of this displacement vector in that direction, right? So if you resolve this along the direction of the interface, it's going to be in that direction, right? And similarly, if I take this displacement vector and resolve it along the interface, that's going to be in that direction. So in other words, a point on the block is going to be moving in that direction at this interface. And similarly, a point on the block is going to be moving in that direction at the interface between the wall and the block, right? And this then allows us to evaluate the relative movement. For example, if I take a point right there on the wedge, right, the relative movement of that point with respect to the block is going to be in that direction, right? And the frictional force is going to be one that resists that relative motion. So therefore, the direction of the frictional force on the wedge at that interface is going to be that. That is going to be the direction of the frictional force, right? Following this approach, now you can see it's pretty easy to mark the direction of the frictional forces at these interfaces, right? So these are the directions of the frictional forces at these interfaces on the respective bodies, right? Following the same approach, these are the directions of the frictional forces on the interfaces for this problem where the block is being lowered. I'll let you figure these out on your own. Now keep in mind, this is an important step in frictional problems. Our second step is to draw the necessary free body diagrams, and you can see there are two rigid bodies that we are considering. One of them is the wedge, the other is the block. So we go ahead and mark the forces acting on these two rigid bodies, right? Keep in mind that there is no need for us to consider moment equilibrium equations, and therefore the locations of these forces at the interfaces are irrelevant. It's not important for us. So I treated this as interface 1 and this as interface 2 and this as interface 3. We already figured out the directions of the frictional forces, right? So we'll start with those first. So F1 is going to be acting vertically down like that. F2 is going to be acting in that direction on the wedge and in the opposite direction on the block. F3 is going to be acting from right to left on the wedge at this interface, right? And these are the directions of the respective normal forces on these interfaces. While the weight of the wedge is neglected, there is a weight for the block. So let's go ahead and mark that as well. While the locations of these forces are not important, but the angles are important, the directions are important. So let's go ahead and mark them properly. These are the corresponding free body diagram for this problem where the block is being lowered. Once again, I'll let you try to understand these on your own. Our third step is to develop a strategy for solving the problem, right? So as part of this, we're going to go ahead and list all the unknowns and we're going to figure out how we can develop the equations necessary to solve for these unknowns, right? These are the unknowns for the problem of lifting the block. We have a total of 7 unknowns, right? We can write down 2 force equilibrium equations for each of the 2 blocks. So that will give us 4 equations. And we also have 3 frictional equations, 1 per frictional interface. So that gives us a total of 7 equations, and therefore the problem can be solved. We have an identical situation for this problem as well. There are 7 unknowns, and we can come up with 7 equations, 4 on the basis of equilibrium, 3 on the basis of friction, and therefore the problem can be solved. Now let's go ahead and write down the equations. And here are the 2 force equilibrium equations for the block for this problem of lifting the block. And here are the 2 equilibrium equations for the wedge. And here are the 3 frictional equations, 1 per interface, right? Let's go over at least one of the equilibrium equations here. Let's go over this equation number 1. By Newton's law, we know some of the forces in the horizontal direction should be equal to 0. So here I am summing up the forces in the horizontal direction from left to right. And we're going to set the sum to 0 over here, right? And this equation is for the block, right? Alright, so let's start with this force right here, N2. N2 makes an angle of 30 degrees to vertical, and therefore the horizontal component is going to be N2 sine 30, and it's going to be directed in the positive x direction, if you will. In other words, going from left to right. So it goes in as a positive term over here, N2 sine 30. And then let's take F2, and this angle right here is 30 degrees, and therefore its component in the horizontal direction is going to be F2 cosine 30, and that's going to be directed in the positive x direction as well, right? And W is perfectly vertical, and therefore it does not have a component in the horizontal direction. F1 is also perfectly vertical, and therefore it doesn't have a component in the horizontal direction. N1 is perfectly horizontal, but it's acting in the opposite positive x direction, and therefore it goes in as a minus term in this equation. So that's going to be minus N1. That's it. Those are the 3 terms in that equation, and you set that to 0. So that's our equation number 1. The remaining equilibrium equations are written in a similar fashion, easy to follow. I'll let you go through on your own. Our first frictional equation is written for interface number 1. The frictional force F1 and the normal force N1 are related by this frictional equation. F1 equals mu, which is the coefficient of friction for that interface, which is given as 0.2 multiplied by N1, right? And similarly, F2 equals 0.4 times N2, F3 equals 0.5 times N3. And these equations are written in a similar manner. Now it's a matter of solving these equations simultaneously in order to find values for the unknowns. But we are mostly interested in the force P, right? So we'll keep that as the objective here. I repeated the seven equations from the previous slide here, so it's kind of convenient for us to look at these and solve. So you just have to look at these equations, come up with your own strategy to solve for the unknowns, which is P here, right? So here's my strategy. Well, P appears only in one of these equations, right? Which is equation number 3. So if I can find N2 and F2 and F3, then I can find P, right? But F2 is related to N2 by this frictional equation, right? And F3 is related to N3 by this frictional equation. So in other words, if I can find N2 and N3, then I can find P. Now if I take equation number 1 and relate F2 to N2, I can come up with an equation for N1 and N2, right? So that'll be one equation in terms of N1 and N2. So that's what equation number 8 is. And similarly, if I take equation number 2 and express F2 in terms of N2 and express F1 in terms of N1, I can come up with one more equation in terms of N1 and N2. And that's what equation 9 is. Now I solve these two simultaneously and I get a value of 8,051.5 Newton for N2. Remember, that's one of the two unknowns that I wanted to first find, right? N1, N2 and N3. So let's go ahead and find N3 now. So I take equation number 4 and express F2 in terms of N2. Then N3 is going to be in terms of N2. So that's what's going on here, right? So N3 works out to be 5,362.3 Newton. So the final step of my strategy is to take equation number 3 and find a value for P. So P equals N2 sine 30. I bring this to the right side, right? And then I express F2 in terms of N2 and bring this to the right side, and express F3 in terms of N3 and bring this to the right side. And I have this equation, right? So now we have values for N2 and N3. Substitute those, and I get this value for P. So we have a block weighing 4,000 Newton, and for the geometry and the frictional coefficients given, we need 9,496 Newton in order to lift that block. So the force needed to lift the block is more than 2 times the weight of the block. Now for the problem of lowering the block, the steps are similar. We end up with this value for P. So for the force needed in order to lower the block is less than half the weight of the block. That's it. We have solved the problem.